Well, hello friends. Merry Christmas. Before we begin today's video, I'd just like to say thank you to everyone who's been hanging out with me this year. Thank you to all of the subscribers, the patrons, the GitHub sponsors, the PayPalers, and everyone else who's been supporting the project in all kinds of different ways. It's been absolutely amazing to have so many people take an interest in what I do, and I hope that we will continue to do interesting things on this channel. So thank you very much for your continued interest and support. Now, today we are going to work on the kernel in Serenity, and we're going to be implementing two things. First is going to be this thing called physical address extension, which is an x86 CPU feature that it's really for allowing you to use more than 4 gigabytes of RAM in a 32-bit processor. But the second part that we're going to implement, and this is really the point of it all, is this thing called the no execute bit. And the no execute bit is a special bit that you can set to control whether a piece of memory can be executed as code or not. And what this will allow us to do is it will allow us to prevent data from being interpreted as code by the processor. And this is a very important, very good security and correctness mechanism that any kernel should have, really. And we don't have this yet. And the reason we don't have it is because it's not supported in the sort of standard 32-bit paging setup. But if you go 64-bit, it's very easy to set it up. But we can also go in 32-bit. We can implement physical address extension support, and then that will also give us no execute bit support. So what we're looking for is really the no execute bit. I don't care super much about being able to use more than 4 gigs of memory at the moment, but we're gonna have to do PAE, as it's called, to get the NX bit, as that's called. So let's look at physical address extension. Or maybe I should explain how paging works at the moment. So what paging does, let me just get a little text file here or something. Oh, I had a perfectly good terminal here. So what paging does is that when you look up some address, when you give the CPU an address of memory, say that you tell the CPU its cool address like I don't know, like like that. Okay, so you're giving this address to the CPU. Now, there's RAM inside your computer, right? But it's the RAM inside your computer is just this big thing, and you might not want to access it exactly the way that it's laid out physically. So instead, what you do is that you chop up all of that physical RAM into this thing called pages, and one page is on Serenity, at least, it's 4 kilobytes each. So it gets chopped up into these 4 kilobyte blocks, and then we use this thing called paging, where we create a virtual address space, and every process has its own virtual address space, and then we chop that up into 4 kilobyte pages as well, and then the CPU has this big table that maps a 4 kilobytes of virtual address space to the 4 kilobytes of physical memory. And you can actually do quite interesting things with that. And you can also it not only points to the physical memory that is used for each 4 kilobytes of virtual memory, but it also has things like access bits, like is this readable, writable, executable, things like that. Is this cacheable? Is this present or not present? And has this been accessed since last time I modified the page metadata? Things like that. There's all kinds of stuff that is stored for each 4 kilobyte page of virtual memory. So this here would be a virtual address, and say that we go to the page table, which paging, and this will turn it into a different address completely. So physical, say that it's stored at physical address 4000 in the computer instead, right? So the point of paging is to figure out for any virtual address, and when you're writing user space programs, you're always using virtual addresses. You never think about physical addresses. The only software that cares about physical addresses is the kernel. So user space only ever sees these virtual addresses. And for instance, when we look at some process here in the system monitor, we look at all the memory maps. All of these addresses here are virtual, and the kernel has internal page tables that convert the virtual addresses to physical addresses. So anyways, that's just a very quick introduction to how that works. Of course, very, very simple. So the way that we have it set up right now is we're using like standard or legacy or whatever 32-bit paging, which means that you have each process, or each thread actually, but each process really has a page, what's it called, like well, we have this register called the CR3, which is control register 3. It's a CPU register that points to the page directory base, I think. And in the page directory base, we find a list of, I think it's 1024 page directory entries. So, and in each one of those, there is 1024 page table entries. So each page table entry controls 4 kilobytes of RAM. Each page directory entry controls 4 megabytes of RAM, and page directory base controls 4 gigabytes of virtual address space. And it's all about the amount of virtual address space that's controlled. So in fact, the same page table entry could, or multiple page table entries could point to the same physical page. It's perfectly possible to share physical memory between many virtual addresses if you wanted to. But for the physical address extension, we're going to have to switch this scheme up a little bit, because no PAE, no physical address extension. The PAE, the CR3, is the page directory table, I think, and it is a 4 pointers to directories. 4 pointers to page directories, yeah. And then we have 4 page directories, control 1 gigabyte each. And then we have 512, I'm confusing myself with my layout here, but 512 page directory entries, and they would control 2 megabyte each, and 512 page table entries controlling 4 kilobytes each. I think that's how it goes. So the important difference between PAE and no PAE and PAE is that 32-bit physical addresses, and for PAE we have 64-bit physical addresses, and this is what makes the layout of the page table change, because now we can only fit half as many addresses in the page table and in the page directory. because they're 64 bits each. Anyway, I realize that I'm probably not explaining this super well, so we're just going to get to the implementation instead. But I just wanted to show you like a little bit of a layout of how these things look that we're going to make. So this is what we currently have, and we want to make this. And then the no execute bit is part of the page table entries or the page directory entries, but it's the highest bit. So currently each page table entry is 32 bits wide, but so we don't have the like the bit number 63, right? We don't have that in each entry, and bit number 63, it's the no execute bit. That's why we can't use it right now, because it's not there. But when we go and we turn these things into 64-bit physical addresses, then we will have that 63rd bit that we can use. So let's just keep that around. I hope I wrote this out right, but I think so. Maybe I'm messing something up here. I'm not sure if I'm doing this completely right, but I think so. Anyway, so the first thing we're going to have to do is we're going to have to turn our page directory entry and page table entry classes into 64-bit things. So we have these, where are they? Here, page directory entry and page table entry, and just these convenience classes that sit on top of the these page tables and allow us to query different flags and stuff. And internally they're just a raw 32-bit value, but now we're going to have a second part of this value, so this will be like the high bits, like that. Or we can actually just do a U64 maybe even. It's probably fine too. And do we ever use that? I don't know. And then for, yeah, these are now 64, and this one is also 64. Now, of course, these static asserts here change because we're changing the size of these guys to be 64 bits instead. And this, I guess, should be a U64 as well. And then let's go and put in the no execute. So that's 1-63. Oh, can I do this? Yeah, I don't want to mess with that right now. We're just gonna say bool is execute disabled. Return raw and okay. And for this guy, we'll do like set bit B. Okay, and I think we'll need the no execute bit exists both on the wait, can I just put this up here? Yeah, that's nicer. Okay, so we'll do that, and oh, should we say that it's a ULL? All right, so now we have made these be 64 bits. Of course, the we're not going to implement 64-bit physical memory. We're just going to stick with our 4 GB limit in Serenity for now, because we're only after the no execute bits. So no execute, highest bit in the page directory, and the PDE and the PTE. So it's the page directory entries or the page table entries. No execute. That's the guy that we are after. So what we want to do now is wait, what's going on here? mraw. Page tables. We don't want to cut off the top of the thing here. You know, maybe this, or no, this is okay the way that it is, but we are anding only keeping the bottom here, so we want to keep the top as well. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, that way. And then, yeah. Just make sure that we don't get rid of that bit. And, okay. Now, next thing we have to do is, because of the, this is one additional step here, right? So previously, we would set up each process to have a page directory base that we would, each process has one of these page directories, right? So I'll show you process, page directory. Every process has a page directory. It's a page directory object, and it's shared between all the threads in the same process. And the page directory has the CR3 value, which is the directory page. So this directory right here is managed by the page directory object in the kernel for each process. But now we want to add one a step of indirection here. So we want to, let's see. I guess we want to have a separate page, physical page of a, we want to have like a directory table, and then there's going to be 4 directory pages or page directories. So the directory table is this 4 pointers. So it's 4 times the 64-bit, so 32 bytes. But I suspect that this needs to be page aligned, so we're just going to put it on a separate page called directory table. This will be the, yeah, this one. And we have to make sure the CR3 points to that. So previously CR3 would point to the single directory page, but now it's going to have to point to the directory table. And then this is going to have 4 pointers inside it. So we will, I think we will define something for that. We'll make a class here. Page directory table. And this would have, like, I guess the easiest thing to do right now is just raw, something like that. So that has, it's these 4 page directory pointers, and then we can also do like can have like a little convenience function here, like page directory entry, no, directory with index, and this will be this as an address. So page directory entry raw index. I guess we'll and off the bottom part. So something like that. Does that make sense? We'll see. We'll see if this works out. Okay, so now what we want to do is we want to set up the page directory object so that it has these members are good, but this is no longer accurate because CR3 is not an array of page directory entries. So instead, what we want to do is probably page directory table. Call it like table. And page directory table CR3. Okay. So, by the way, the reason that we're able to use raw pointers to these things directly is because I have these special reserved pages for the kernel that are identity mapped, and I use them in paging right now to make things a bit easier. And that means that they are identity mapped, meaning that their virtual address is identical to their physical address. So normally that's not the case, but I do reserve some pages for use in the paging code just to make it a bit easier, because then you don't have to do translation between virtual and physical when you're working with paging itself. But longer term, that's probably something that we're going to want to change just to have more flexibility. But right now, it just simplifies things because it allows me to just take this physical address here and just cast it to a pointer, and I know that it will work, and it will work because it's identity mapped. Otherwise, it wouldn't have worked, in case this was confusing to anyone. So let's see. I think we are good with that. Now, the way that we set up paging in so every process has its own page tables, right? But there's also a shared page table. It's called the kernel page directory, and it's held here by the memory manager object. And the kernel page directory manages the bottom 8 megabytes of the address space and the top 1 gigabyte. And here actually is where we create page tables. We have these hard-coded page tables for the bottom 8 megabytes. That's where we keep these identity map pages that I was just talking about. And we also have the null page and some other stuff like kmalloc lives there. And first thing that we notice here is that these are actually gonna, because we can only fit 512 page directory entries in each one, and they control 2 megabytes each. Each of these guys control 2 megabytes each, yeah. That means that to control the bottom 8 megabytes, we're going to need to have 4 of these rather than 4 rather than 4. Wait, what the hell am I saying? We're going to need 4 rather than 2. So really we need like this. This is getting kind of repetitive. Also, this hat is really warm. Let's see. So I think we can call these low page tables. We'll just do that instead, because now we're getting more and more of these. So page table 0. Let me just see how we do this. So obviously we can do this in a loop, but I just want to write it out so that we see what we're doing here. So this actually goes into this reserved physical address that we have for the kernel page tables, and we set that up in the little boot assembly program here. We actually reserve space for some page tables, and this is just so that the bootloader knows not to stomp on this memory. We want them to have like reserved memory for those kernel page tables. Now we're going to need to increase this because we're going to need an extra page for this, and then we are going to need previously we had 1 page directory, now we have 4, so we're going to need 3 extra here, and then here we need 2 extra because we want to control the bottom 8 megabytes. So that's that's 1 extra, 3 extra, 2 extra, so 6 extra. So we will take this up to 9 here, which just means that we're reserving space for 6 extra pages of 4 kilobytes. And the way that we pass this is just we just like make an empty buffer in the assembly program here, and then we pass the address of the base of that empty buffer to the init function. We're just passing it here. So if we look at init cpp, we shall actually see that we get this physical address for kernel page tables. It's passed to us when we first enter C++, and then we pass that along to memory manager initialize. And he passes it to the constructor, memory manager, right, and this is where we are. So we have this address here. This is the address of that buffer in boot.s that is now 9 pages wide. And we can just index into it like this. And I guess these were called page tables. Okay, and of course, when we create the page directory itself is going to be bigger now too. So it's going to, previously it would just take up the 1 page. This was the page directory previously was 1 page that had 1024 page directory entries. But now it will be 1 page that has these 4 pointers to page directories, and then it will be 4 pages that have each page directory in them. So basically what we're setting up here, you can sort of see it, that although it's just a coincidence that this is symmetrical. So never mind that part, I was just getting carried away. But here you can see it. This is the directory table, and then the 4 directory pages. It's these 2. So when we create at a physical address, create a fixed address, we call this constructor here page directory. So now we want to have the directory table at the address we are given, and then we want to make some additional things at offsets into this. So I guess this is just taking a physical address and offsetting it by 1 page. It's a supervisor page. You may not return it to free list. So 3. Okay, so now this means that this address that we are given, we chomp up 5 pages from it. which actually means that in memory manager, this guy will eat 5 pages here, so we got to start at an offset. So he ended at offset by 4, so we got to continue at 5, 6, 7, 8. Okay. And then let's see. Then we call initialize paging, which goes down here, and these mem sets here, let's just do them up here. Keep them closer to what we're doing. Now we can use loop. I just zero these out, and yes, we can actually do the allocation in a loop as well. So we'll say I, and I guess it's I plus 5. Something like that. Cool. Okay. Now in the page directory, oh man, how do we want to set this up? So page directory, we got to point these things at something. So we had table. This here gives us a page directory table pointer to the CR3, which is the directory table. So this gives us a typed pointer to this, right? And then we want to point the, wait, what do we have here? Oh, right, so that's 4 entries. So we get the first directory. Wait a minute, how the heck does this work? Page directory table. Oh, it has 4 rows inside of it. So I don't need to index into it. I can just do this. In fact, I guess we could even have this return a amp. Okay, so table dot directory zero. So there are 4 directories. They each control 1 GB of virtual address space. So the bottom, this is the first gigabyte, 2nd gigabyte, 3rd gigabyte, and 4th gigabyte of address space, right? So directory 0. How does this work? Directory 0. We want this to point there. I guess we just have to update this value. So in fact, it's going to be table.raw 0 is m directory pages 0. Physical address is pointer. And I'll turn that into U64. Does this make sense? So now these guys are just pointing this 4 entry table, right? Because you can't have more entries, because you would tell us index 4 is past the end, right? M directory pages, and I think, let me get the documentation. I think that there's a bit somewhere in this table you have to set for each entry to tell the processor that it's like a live entry or something like that. So I'm paging PAE. So CR3 reference is the base of a 32-byte page directory pointer table. That's right. And this is a page directory pointer table entry. So I guess that's what this is. This is the page directory pointer table. We're just calling it page directory table. I guess we could rename it to pointer table. Then we're consistent with the manual. So right now we're just slapping the address of each page directory directly into this, but it has a format. So this is what we're using here, the physical address of a 4 kilobyte aligned page directory. That's this guy. And this must be 0, cache disable, cache write through, blah, blah, blah. And this guy right here has to be 1. So we have to set these to 1. It's just the 0th bit, so we can just do like this. Okay. So this is setting up a page directory at a specific physical address, but this is only used once by the kernel's own page directory. Then we also want to set up page directories whenever we're creating a process. So that works a little bit differently, because in those cases we just want to allocate physical memory from the page allocator rather than using a hard-coded address. So that's this constructor right here. So we'll just do something very similar. We'll do like a physical page, or no, allocate supervisor physical page. And in fact, we can just allocate a bunch of them. So for the bottom 3 gigs, we'll do this, but actually for the top 1 gigabyte of memory, we can just get the kernel page directory and get his directory pages. We can just point to them directly. It's actually kind of nice, because currently we have to lazily, we have to keep that in sync always, because we've been having like a copy of the top 1 gigabyte of address space. Since that's used by the kernel, then we have to like duplicate that in every process, and that has been the source of bugs sometimes, that we fall out of sync. So this allows us to directly have the top 1 gigabyte be controlled by the exact same page directory that the kernel uses. That's really good. And of course, the reason that it works that way is that, I can show you that the way that the address space is laid out in Serenity is that 1 gigabyte user space, 2 gigabyte user space, or we should write it this way. But anything above 3 gigabyte kernel space. And there's an exception here actually, so it's more like the 8 megabytes. Everything above 8 megabytes, above 1 gigabyte too, because the first 8 MB is kernel space. It's kernel space. How do you type when a funny E like that? I don't even know how to do it. I don't know how to do it. Anyway, I have a US English keyboard. It's not set up for your accents and things. So we got to do this as well in the down here. Just setting up the pointers so that the PDPT points at each individual directory page that we've set up. Now, it's calling populate page directory, but the purpose of that is to take the mappings for the bottom 8 megs and the top 1 gigs and copy those from the kernel page directory into every new process. But we don't need to do that anymore for the top 1 gig, because we get that for free here, because we can just use the same exact page directory. But we still have to do it for the bottom the bottom 8 megs. So let's see how we do that. Directory page allocation. We've already taken care of allocation. So copy from, we don't need this. Okay, so we want to, oops, I'm knocking over my teacup here. The bottom 8 table dot directory. So this is all in directory 0. And what is in there? It's a page directory entry. And we want to copy the 0th entry from, I guess we can get rid of this batch requirement here, or we can say that you need a page directory batch, rather, class page directory. Kernel page directory dot table dot directory. So copy the, it's 2 megs per entry, so we gotta copy 4 entries. Clone bottom 8 megs of mappings from kernel page directory. Okay, so this is only needed when setting up a user space page directory, which is what this is. Share the kernel only mappings. It's C00, like that. And so yeah, now we're cloning those, and memory manager. Get rid of that populate function, and I guess actually now that we explicitly share, or we always share the top 1 gigabyte, then we can get rid of the page fault mechanism for that. So handle fault, handle page fault. So previously we had to take care of this. If we ever got a page fault in the top 1 gigabyte of RAM or virtual space, then we had to check, oh, is this just because you are out of sync with the kernel page directory? And if so, we would copy from the kernel page directory to the current process page directory. But now that these are always just shared by default, we can just not do that. So it's really nice. And then we also have this thing that explicitly updates these mappings, which we can also get rid of, update kernel mappings. We don't have to do that anymore because these are just for free. See, this ensures that the blah, blah, blah is up to date. It's just a mem copy of the upper 1 GB of page tables, so we can just not do it. That's actually really, really nice. Now, let's go and look at Memory Manager. So when we are setting this thing up at boot, now we have created ourselves a page directory, hopefully, and we have the bottom 8 MB of page tables at hard-coded addresses here. We've cleared them out, and now we're going to initialize paging. So the bottom 8 MB. We are identity mapping them. So here is where we iterate one page at a time through the bottom 8 MB. And we go one page at a time. You can see here, offset plus page size. So for each step, we ensure PTE, which ensures instantiates a page table entry if one does not exist. And this is the function where page tables get built sort of incrementally by the memory manager. So I think this is going to be where we have to do most of the work to make this whole thing come together. So this is how things work in the old layout. So can we get a picture of this or something? Do you have a picture? So this is the layout of an address when using PAE. But let me see if I can find. Oh crap! Can we see the old layout, the one that we're currently using? Right. So this is what we're currently using. Currently, we've been doing 4 KB pages using 32-bit paging. So each virtual address, or linear address as they call it in the Intel manuals, which by the way is what I used to call it in Serenity, but then I changed it to virtual because everybody knows what a virtual address is, and not as many people recognize linear. So the bottom 12 bits of a virtual address that you're using in your program, they are just the offset into the page. So they just point into the page, as you can see here, 4 KB physical page. But then the next, 10 bits, they are an offset into a page table, basically. So an offset into a page table pointing at a specific page table entry. And then the top, however many bits that is, because math is apparently difficult for me right now. I guess the top 10 bits are the pointer into the page directory. So they point at a specific page directory entry. Now, this whole setup means that each page table and page directory has 1024 entries, but now we were changing it so that they only have 512 entries so that they can be 64 bits each. That means that the address layout changes slightly here. So the bottom 12 bits are still the offset, but then we are looking at, I guess, 9 bits instead. 9 bits of page table address or index, and then 9 bits of page directory index, and then 2 bits of page directory table pointer index. So the top 2 bits, page directory table index, is the virtual address And we gotta go, I find these things difficult sometimes. 30 steps and with 3 to get the upper 2 bits. And then these change. This one doesn't change because it's still 12 bits here, but we have 1 less bit, and then 1 less bit, and then we only move this 1 less step, right? Yeah. Okay, so and then and then this stuff here is, we have to extend this, but anyway, we got to find the page directory entry that we are interested in. So I guess it's the page directory table, and then we want the directory number, page directory table index, and then we have the page directory index there. Okay, I think that gives us the page directory entry. I think. And then this is where we, this is for the bottom 8 megabytes again, where we, like, if the page directory index is 0, then we make sure that we use page table 0. But they should instead be if the page directory table index is 0. So if we're in the bottom 1 gigabyte of Azure space, and if it's less than 4, okay. Yeah. Okay, so if less than 4, then use the low page tables page directory index, and then we can get rid of this branch here because it's just doing the same thing. And I don't know why we have a commented out assertion here. Let's just not have that. Okay, so now we compute the, this is the directory pointer, directory table, and this is the directory, this is the table. Directory table, right? And then the offset is irrelevant because the purpose of this function is to make sure that there is a page table entry somewhere that we can modify. Okay, so I think this is probably good. Maybe, I hope this is good. Okay, so initialize paging. After we set all of this stuff up, and if we did everything correctly, then we have to turn on paging with the paging address extension, physical address extension. So we turn that on with the PAE flag in CR4. So bit 5. And I screwed this code up like twice yesterday, so I'm just gonna be super obvious now. So hex 20. I'm gonna turn on PAE, which I know that we don't have to set it this way, but we're setting it this way now just for clarity. You can combine these into a single thing, obviously. And well, this is probably not going to be enough, but I guess I would just like to see what it is that we're missing now. Okay, well that booted. Okay, so did we do everything correctly? How the hell do we even know? I mean, I assume. Okay. Can close processes. Can play sound. Don't hear much because the volume is low, but we can do something. Can we change the theme? Check out the dark theme I've been working on, by the way. It's pretty neat. In fact, let's make that the default theme for today. So let me just copy this into my root home and on. And change to a dark theme by default. Very important. Okay, so this actually appears to be booting up. That's pretty awesome. I thought we were going to struggle way more. It's the WX bit all over again, or what's it called, WP. But there's probably something I'm not doing right. So can we set the no execute bit maybe on something? Let's try it. So I guess we could, or well, let's just commit this, assuming that it's good. Kernel, switch or enable PAE. More advanced. Or it's not, well, whatever. This will give us access to the NX no execute bit, allowing us to disable prevent execution of memory that's not supposed to be executed. Introduce a one more indirection layer in the CPU indirection layer in the paging code. The what was it called? The page directory pointer table, PPT. Each page directory has four separate page directory arrays. Governing 1 GB of virtual address space each. a VM each. A really nice, neat side effect of this is that you can now share the directory the physical page containing the 3 GB kernel only address space metadata between all processes instead of lazily cloning it on page faults. That's really neat because that was causing bugs. Just found some issue with that just yesterday. I think Conrad was working on something, and then because I was familiar with the code, and it was like kind of obvious to me what's happening, but for someone who's not familiar with that mechanism, that's like a Serenity specific mechanism. It's super. It was super opaque what was going on. So this will be way better because now the kernel page directory is just mapped all the time. There's no clones of it. Everyone has the same exact physical page using for it. But of course, the bottom 8 megabytes is still cloned. But at the moment, we never actually change anything about those. Whereas in the top gigabyte, we allocate, deallocate stuff, so it keeps changing. Anyway, so let's see. What if we wanted to do the no execute bit then we would say, what do we call it? Execute disable, right? Is set execute disabled. So we want to call this whenever we are mapping a region, say. Then do map, remap. So when we're taking a VM region, and damn it, where's the code that maps the region? Here it is. Here's unmap. This unmaps the region. Remap page. Okay. So when we're remapping a specific page, we just want to say, so currently it's setting the present flag at the writable flag based on the writable state of the region. We can also say set execute disabled is executable. Okay. And this is for remapping a specific page, but then we also have a function that maps the whole region. So I guess we should just do the same thing here. So set execute disabled is executable. Okay, so will this still work? Because I guess we'll find out. That does not work. Instruction fetch. It sounds like we are getting a instruction fetch page fault, which I guess is this mechanism working as intended. Because you're reading from this address, and it's an instruction fetch that triggers it. Page, how does this work? Page fault. Who's printing this? Is this code right here? Yeah. So, undercover page fault, read from this address. So we are crashing because we can't execute? but this is this is just weird because this is the elf loader. So we're trying to load a program to execute, and it looks like it's crashing when just parsing the elf binary. But it's saying that it's an instruction fetch. And this is where we usually load the elf binaries. So wait, what the heck? Let me show you what I mean, by the way. Let's execute disable. Let's just make it bootable. So normally, if we look at some program like Windows Server, then we can see that his elf binary is loaded at this address here. So 100, 1000. And that's just where we set up the elf in memory so that we can load it or parse it. But now we are trying to read exactly from 100, 1012, and it's killing us. But we're just trying to read. We're not trying to run that as code, because this is just elf header. So what the frick? Tell me about your page fault exceptions. Okay, so our page fault has exception code 9 at this address. So this is the error code right here. So 9 is 1 for page level protection violation, and 8 is for instruction fetch, but this is not the same bit. That's the 8. Reserved bit violation. The fault was caused by a reserved bit set to 1 in some paging structure entry. Fascinating. So we've set a 1 somewhere that we were not supposed to set. Well, we've only changed 1 bit, which was the no execute bit, so I guess it's reserved. Maybe we have to enable it somehow or as a feature. But let's fix that. So I had this wrong. So it's actually, this is reserved bit violation, and this guy was the next bit. So it's kind of an interesting error, actually. I haven't seen it before. So I'll print that out too. Reserved bit violation. Okay, and it's nice that the this seems to have worked out really well. Hopefully, but I think I got everything right. But let's see. We'll know it's right if we can make the no execute bit work. Okay, so now at least we're saying reserve bit violation, read from address, blah blah blah. So we can at least commit these changes. Not these changes, but the these changes. To learn my aliases. GS GD cached kernel. You're misinterpreting. Interpret reserved bit violation page faults correctly. We don't actually react to leaves in any meaningful way other than crashing. But let's at least print the correct information. Okay, so, but why are we violating some reserve bit? If there's no translation because a reserve bit was set, but we want this guy. This is the one we're interested in. So it's set if the access causing the page fault exception was an instruction fetch, and either CR4 SMEP or both PAE is on and NXE is on. So this one is on. So this would be set either if this is on or this is on. I don't think we're setting either of these two anywhere, so what is SMEP? It's supervisor mode something, execute protection something something. And this PDF viewer is so slow. Like, it takes seconds sometimes when you press page down. Show me the SMEP. Supervisor mode execution prevention. Access rights. SMEP. Do we have this on x86? SMEP. When did it come? Wait, hold on. SMEP Intel introduced 2011. All right. And so it was either SMEP or what was the other one? It's like NEX or something. Either SMEP is one or PAE is one, which it is, and NXE is one in this thing, this register. So I want to pick whichever one's older, right? So if this one, I mean, I didn't really do an exhaustive search, but like if this is like some 2011 thing, if EFFER is a bit older, that's good. EFFER, add an AMD K6. Well, that's kind of old. Yeah, very old. So I don't know which one. We should use one of them, I guess. So it's model specific register C80. How the heck do you read these again? Read model specific register. Read MSR ECX into EDX EAX, right? So if we wanted to set this register, we would just what the heck was that? Can we find FR somewhere? Control registers. I just want to see it. FR MSR. Okay, I want to know about that. No? Man, searching in this document viewer. Oh, come on, guys. Maybe we should build a document viewer. Oh, not today. Okay, what the heck was the... This is the MSR number. All right, well, we'll just take their word for it and put that into ECX. Then we'll read the register, and then we will have it in EDX, EAX. And upper bits are all reserved, so I guess we have everything we want in EAX. And we care about this bit right here. No execute enable. Doing the hard part with Python here. So hex 800. Damn it. EX. And then we just write it back, I think. I think that's how it works. You can just yeah, it's just symmetrical. So you just read, modify, and write it back. And I think that will just set that thing. No, too many percent signs. What was I thinking? I am no master at GNU assembly syntax. I just add and remove percent signs as I go. And we booted, by the way. So that's pretty cool. But wait, did I comment out the... No. Oh, okay. So we got to test this. So what if we say that we will load some program with a ridiculous permissions. So mdo exec. Well, we map process here. So we can screw up the exec bit if executable and name is not ID. So if the name of the process we're loading is ID, then we won't set the executable bit when loading. See what happens? No, that didn't work. All right. Maybe that was a bit too... Oh, wait. Name here means something else. It's the name of this segment or section. I guess we want path. So let's do path instead. Path is not bin ID. It's a very silly way of testing. I just want to see. Okay. Well, look at that. So we're crashing at this address. 8004 blah blah blah, which is right here, which is read but not execute. And we crash. That's pretty fucking cool. Okay, so let's see. I think we can commit this. And we'll say kernel implement or use the CPU's NX bit to enforce prompt exec on memory, I think. Now that we have PAE support, we can start crashing. We can ask the CPU to crash processes for trying to execute non-executable memory. This is pretty cool. Let's be honest, it's pretty cool. I feel like we should make a little crash. So we have the crash program, it just crashes in all these different ways. So let's make another way of crashing. Execute non-executable memory. And maybe this will be a large X. Okay, so how are we going to crash creatively now? If mode is execute non-executable memory. I guess we will grab some memory. We'll ask for page, prot read, prot write, map anonymous, map private, no file descriptor, no offset. Just check that it worked out. Oh wait, it's called mem. Let's call it putter instead, because putter is a nice name. Okay, and then I guess we can just put a, I don't know, put like a ret instruction. What is that, C3? I think we'll do that. And then can we just call it? We can just call it, we will just do like, oh man, I always forget how you cast to a function pointer. Frickin' hell. I mean, okay, wait, I can do this, come on. Do I have it somewhere, please? No? Okay. Func. Okay, how the hell do you do it? I always forget. It's void something, you absolute jerk. Okay, I'm just standing still. Type def. This is the silly. I've done it before. I promise, I've done it before. Somehow it's like, it's just not sticky. It doesn't stick to my brain. I don't know why. Crashy function putter. Putter. There we go. Okay. Now, we should just crash because this is not executable. And if we map it with prot exec, then everything should be fine. So crash X, segmentation violation. We cannot instruction fetch from here, so it's a no execute crash, legit, at this address. 143, Very cool. And then what if we map it prod exec? Then we will assert not reached. Because, yeah, we're just asserting here because we actually returned. We're not supposed to return. That's pretty good. So let's crash. Oh, wait. I gotta do the be a good boy now and write a man page. Or we already have a man page for crash, but I gotta add this option. Execute attempt to execute non-executable memory. Prot exec not mapped at prot exec. Just see that it looks nice. Oh, and actually should fix this usage string here. It's been lagging behind a bit. SX, missing these up here. SXYX. It's not the most important thing in the world, but you know, it's the little things that matter. Just see how that help page looks like. Crash. Ooh, by the way, I should probably make the help documents have a different color when you're using dark theme. Anyway, attempt to execute non-executable memory. Very cool. Crash X. Assertion failed. Yeah, but that's just because we didn't rebuild after I unbroke it. So let's just double check. And there we have it. It's a frickin' no execute bit support in Serenity. How cool is that? And isn't it nice that it wasn't super difficult? It just took a decent understanding of what I wanted to do ahead of time. And just sitting down and doing the work. So crash, add X option. For attempting to execute non-executable memory. Great. I wonder if we allow you to map writable and executable memory. Maybe we should just not let you. Oh, no, not that flags. Prot. Prot, right? And prot exec. What happens if you do that? If you just refuse? I wonder. And same for mprotect. Oh, this thing should actually have set executable. Prot exec. But if you try to set both, maybe enval? I'm just curious. Maybe we can have a little bit of lightweight enforcement of not having writable and executable memory at the same time. We'll just run, right? Yeah. It's kind of nice. And I think we can do that. So kernel and protect to set up right, exact. Also allow and protect to set a prop exec on a mapping. Yeah. Something we are not allowing. We're just ignoring for. Because we didn't care about it, because prot exec bit was kind of meaningless anyway. But this is really, really cool. I have all these other crashes, all the different ways of crashing. It's fun with the crash program. So I think we're basically done for the day here. So what have we done? We built PAE support into Serenity. So we turned the paging setup from this 2-level or 3-level, however you think about it, but 2 tables basically, page directory tables full of pointers to page table, and turn it into this 3-level or 4-level thing. 3-level. Let's call it 2-level and 3-level because I think that's what people normally do. So 2 levels to 3 levels, and that was pretty smooth. And then we used the fact that now we can set the uppermost bit in the page directory and page table entries to enforce no execute. And then we have set that up so that now memory that is mapped as executable can be executed. Memory that's not mapped as executable cannot be executed. I think this is really, really great, and it's going to help us catch bugs going forward, and it's just the right thing to do. So it's really, really cool. So I think this is going to be it for today's video. So if you made it this far, then I thank you for watching, for hanging out with me while we work on this. And I hope you saw something interesting here today. And maybe even learn something fun about Intel processors or programming or whatever. I'll put this back on now. And I guess again, I just want to say thank you so much to everyone who's been hanging out with me all year. It's been absolutely awesome to do this stuff with you. And thank you for subscribing, commenting, liking, sharing, all of those things. Thank you to all the supporters on the different donation platforms, all the IRC hangouters, all of the people who talk to me on Reddit, 4chan, Twitter, email, everywhere, YouTube. I've had so many awesome, interesting conversations with so many awesome, interesting people since I started doing this, and I'm really grateful for that. So, a super Merry Christmas to all of you, and I'll see you again soon. Bye.